These are the episodes of the web series Television, our 5-minute mission to explore cool new technologies, to seek out new ideas and new information, to boldly go through the PowerPoint slides. I'm your captain, Mike Yawn. The topic today is CAP theorem, an important principle governing how distributed systems work, or perhaps more accurately, what happens when they fail. What exactly is CAP theorem? It's an acknowledgement of an inconvenient reality concerning distributed systems, that in a world of unreliable networks, hardware susceptible to failures, and other challenges, we must make a choice between offering strong consistency guarantees and being always available. To make any sense of CAP theorem, we have to first define our terms. In the context of CAP theorem, consistency in a distributed system means that whenever data is written to the system, all subsequent reads will see that data. This is an attribute that is more accurately called linearizability. It's a level of consistency above what most distributed key-value stores offer. Eventual consistency is much more common. Consistency in CAP is also not the same thing as the consistency claims of ACID attributes in database systems. So what does it mean to lose consistency, or to not claim it in the first place? Readers on different nodes may see different results based on lag in propagating updates and/or updates applied in different orders on different nodes. Availability in CAP means that as long as some of our distributed nodes are up, a reader will be given a response. The return data may be stale, but the system continues to be available and responsive. A network partition, also called split brain syndrome, happens when the network between nodes goes all wonky. When messages are not received, it's impossible to reliably determine whether the non-responsive node has crashed or the network is just not delivering the messages. If you've ever been ghosted by someone and sent messages just trying to get a confirmation they're still alive, you understand this. Given these terms and the fact that a system can at best provide two of the three attributes, we can categorize systems by which two they claim. An AP system is the most common categorization. AP systems will favor continued availability in the face of a network partition. CP systems may return errors in the face of a network partition. Generally, a quorum mechanism is used so that some nodes of the system may continue to function at normal levels. The subset of a partition system that has the majority of nodes can continue to operate, while nodes that are still up but don't connect with enough other nodes to see a quorum are obligated to reject requests, as they cannot guarantee consistency. This is the unicorn of CAP theorem, the mythical AC system. I've seen this designation applied to systems that run on a single node, but given that CAP theorem is a theorem about distributed systems, it's meaningless to use it to categorize a non-distributed system. For multi-node systems, the AP and CP designations are the only ones that are realistically achievable. Of the two categories we just spoke of, CP systems are trickier to implement. Making a system consistent under all types of failures is really hard to get right. Almost all systems that claim CP are using a quorum mechanism based on one of these two algorithms. Discussing them, even at a high level, is beyond the scope of this brief intro, and it makes my brain hurt, so let's just move on. But if you're really interested, I will post a link to a technical paper on Raft in the notes. Most Hazelcast data structures, including IMAPs, are AP, favoring availability. But there are cases where AP is not the best solution. In Hazelcast 3.12 release, we introduced the CP subsystem, based on the Raft consensus algorithm. A carefully selected set of features was moved from the AP subsystem to the CP subsystem, based on what features tend to require consistency over availability. For example, distributed coordination is an area where absolute correctness is needed. There's not much value in a lock that isn't exclusive, or a countdown latch that loses count. So these critical features became CP. Also moved to CP were atomic variables that can hold references to a long and an object, respectively. In the 4.0 release, we added persistence to the CP subsystem so that the state of CP structures could survive a restart. And in 5.4, we added a CP version of a hash map, which we'll look at in more detail in our next episode. With the changes made to the CP subsystem in Release 5.4, all of CP was moved to the Enterprise Edition. Certain features, like CP persistence, have always been Enterprise features. Because strong consistency involves ensuring that every member has an up-to-date copy of the data, large CP clusters would perform poorly. To avoid this, we subdivide larger clusters into smaller subgroupings called CP groups. Each CP data structure will belong to one such subgroup. For purposes of establishing a quorum, the CP subsystem needs an odd number of nodes. And to keep performance from degrading due to the complex coordination, only groups of 3, 5, or 7 nodes are supported. But larger clusters can designate multiple such subgroups of nodes, each responsible for a subset of the CP structures in use. For developer ease of use, there is the option of running with fewer than 3 nodes. This unsafe mode provides no consistency guarantees, so obviously shouldn't be used for production. The new CP map data structure doesn't have the option to run in unsafe mode, so you'll need a 3-node or larger cluster during development. It would be inconsistent of me to finish without some cluster facts. Distributed consistency is hard. Most distributed systems are AP and offer eventual consistency. CP systems are almost all based on one of 2 distributed consensus algorithms, Raft or Paxos. Hazelcast uses Raft. Hazelcast offers AP for most data structures and CP for structures that have higher consistency demands. In our next episode, we'll take a closer look at the new CP map data structure.